I'm Aurora ROSSI, and today I will talk about my PhD work on computational method and analysis of temporal networks with application in neuroscience. So I would like to start by defining what is a temporal network, and there are several ways to represent time-dependent connection, and one of them is the temporal network. And there are several definitions of temporal network, but in this work we are using the definition that a temporal network is a collection of static graphs. And temporal networks are also suitable to model several real-world data. And in this thesis, I applied them to brain data, and in particular brain data that was recorded with the functional magnetic resonance imaging technique. And during these 3 years, I mainly focused on two research questions. So the first one is the question, is a given brain property statistically significant? And an example of this question is given Alzheimer and healthy brain, which hubs are different. So hubs are different between a brain of Alzheimer people and healthy people. And the second question is which brain subnetwork are responsible for a given property. So given the fact that the hubs are different, we want to understand which of them are different. And so to do that, we use machine learning and explainable AI technique. But this is just an example of application of these two questions. And so the content of the talk of today are four main topics. So we will start with the methodology, so with the creation of the dataset. So we will see how to create a temporal network starting from raw data, raw fMRI data. And then we will move to the second question, and so we will provide a tool to assess if a property of a network is significant or not. And then I will show you an analysis of in which we investigate which brain part, so which subnetwork are important for a given property. And the last topic is machine learning for temporal graphs. So I will show you what is a graph neural network and how apply graph neural network to temporal graphs. So let's start with the first topic in which I collaborated with the CRONOS team here at Inria. And we published two datasets in the research.gov website. So now we will see the pipeline that we used to create the data, so to create the temporal network from the fMRI data. So we start with the output of a fMRI machine, which is a time series for each part of the brain, and in particular is a time series for each voxel of the brain. And a voxel is a 3D pixel of the brain. And you can see that this time series is quite noisy because it can contain some movement of the patient and some also involuntary movements, such as the cardiac one. And so we apply a technique to clean our data, and the first one is a linear regression and bandpass filtering to have a clean time series for each voxel of the brain. And after that, we use a brain atlas, which is a division of the voxel of the brain in some region of interest according to different criteria, such as different functionality or different structure. And in order to divide the brain, we use the brain atlas, and so we average the time series that are inside a region of interest, and so we will obtain a time series for each brain area. And after this, we apply the sliding window method. So we take each couple of brain areas and we take their time series, and then we superpose a window, and within the window we compute the Pearson correlation coefficient, that will be the weight of the edge that there is between the two brain regions we are considering. And we repeat this process for each pair of time series, and so we obtain an adjacency matrix. After that, we repeat this process, and we obtain a second adjacency matrix, because we are again computing all the Pearson correlation, taking account each couple of time series. And so we keep doing this process until we finish to cover the whole time series. And so we obtain a collection of adjacency matrix, and so we obtain a temporal network. So this temporal network has the brain region, so the nodes that are brain region, and it's a complete graph and weighted, so the weights are computed in this way, computing the Pearson correlation between the two windows, between the two time series. And yeah, so this is the temporal network that we obtain. And so using this pipeline, which is standard in the neuroscientific community, we created two datasets. The first dataset contained the RESI state fMRI data from the Human Connectome project of 1,000 of subjects, and the number of node change according to the brain atlas that we choose. So we choose between 100 and 600, and then they have 27 snapshot. And then we also created a label version which contain again 1,000 of subjects, but in this case we also add additional information such as the age and biological sex label. And this dataset was designed to be used in machine learning tasks, and so it was added in the ML dataset.jl package, which is a package that contains machine learning dataset in the Julia community. And we chose to publish these two datasets because in the computer science community it's difficult to find ready-to-use network that represent the brain activity. And in fact, it had in 2 years 135 downloads. So now we move to the second topic, and so we provide a tool to answer to the question, is an observed property of a network significant? And also in this case we collaborated with the CRONOS team, and in particular with Samuel Delon-Rigotier. And so our contribution Okay, so our contribution is providing a new temporal model, temporal null model. And so a null model is a random object that is used to test hypotheses on, for example, in this case, on brain networks. And it's a random object that preserves some properties of the data that we are considering. And in our case, we wanted to match the number of nodes, the number of time steps, the average degree, and the temporal small worldness. We choose to investigate the temporal small worldness because it's one of the two properties that define a complex network, and the brain it's a complex network. And so now I want to define what is the temporal small worldness. So in the static case, the small worldness is the ratio between the clustering coefficient and the path length. And in the temporal case, instead, is the ratio between the temporal clustering coefficient and the foremost path length. And we consider we first consider the static clustering coefficient, which is the number of triangle over two paths. And in other words, we can say that is how much the neighbor of the node are connected. And for the temporal case, we took the average of the clustering coefficient computed within each snapshot of the graph. And instead, for the path length, we chose the foremost path length, which tried to minimize the arrival time of the path length. And in this example, if we want to go from node A to node E, at time 1 we stay in node A, then at time 2 we jump off node B, and then at time 3 we go in the node E. And so this is the representation of the path that I just described to you. In the literature, there were already proposed some null model for brain data, and these two models were introduced by Sizemore and Basset, and they were constructing starting from the empirical data. And both of these two models are permuting some aspect of this data, and the random temporal permuted time graph model permute the time at which each edge occur, and instead the random temporal edge graph model permute one end of each edge within the same snapshot. We consider other models, in particular geometric models. The first two that we considered were the random temporal square graph model and the random temporal torus graph model. So these two graph models are constructed in a similar way. So we distributed nodes, so point on the square and on the torus, and we connect the two nodes if they are at a certain distance, less than a radius r, and so if they are contained in a ball. And in fact, these two graph models are also known as disk graph model, and were introduced by Penrose. And to integrate the temporal dimension, we apply to each point a displacement vector. And this vector, in particular the direction of the vector, is chosen with a uniform probability in 0, 2 pi, and then the length of the vector is uniform distributed in the in minus v and v, which is a parameter. And so we connect again the point, and we obtain the second snapshot. And then we repeat this process until we match the number of snapshots of the real data. The last model we considered is the hyperbolic model. In particular, we consider the temporal variant of the Kyokov random hyperbolic graph model. And here you can see the hyperboloid and its projection in the Poincaré disk. And as before, this graph is constructed by distributing point of an upper half hyperboloid of negative curvature within a disk of radius r. And so the zeta parameter is the parameter that influences the curvature, and alpha is another parameter that influences how the nodes are placed in the space. And in particular, if this alpha is less than zeta, we obtain that the points, so the node, tend to be near the center of the hyperboloid. And if alpha is equal to zeta, then we have a uniform distribution. And then we have that if alpha is bigger than zeta, the point tend to be near the border of the disk. So these are the three random models that we consider, one on the square, one of the torus, and the hyperboloid one. In this picture, you can see the projection from the hyperboloid to the Poincaré disk. And also in the picture of the right, you can see the main difference between the square and the torus. In particular, in the torus, we have that big edges that connect the point. Okay. So these are the results that we obtain. So we first have to think about the pipeline. So the output of the pipeline was a weighted temporal graph, but to apply this matrix, we wanted a binary, so a not weighted graph. And so, given the fact that in the neuroscientific community there is not a consensus on which threshold is the best one, we choose to consider all the possible thresholds, and this possible threshold create different average degree. So that is the reason why so we computed the temporal small worldness for different average degree, because these average degree were created by choosing different threshold values. And you can see in pink and gray the two models from the literature. So this is more Basset model. Then in green and orange there are the two geometric models on the square and on the torus. And then the purple model is the hyperbolic graph model. And you can see that the threshold empirical data are the blue one, and so the hyperbolic model is the one that is most close to the data for different average degrees. So in this work, we propose as a suitable null model the random temporal hyperbolic graph model. And as a future work, we would like to apply this null model for test some hypotheses on the brain, for example, the one I was showing you at the beginning. And then, given the fact that there are two main properties that define a complex network, which one was the scale, the small worldness that we investigate in this work, but the other one is the scale freeness. So we would like to investigate if also this property, and if the random hyperbolic model is still the best model for that measure, or we should consider the Barabasi-Albert model. So now we are ready to move to the next topic, and in particular I want to show you a tool and analysis in trying to answer to the question which subnetwork contribute the most to a given property. And in this case we collaborated with the CRONOS team, but also with the INSERM and the University of Burgundy. So the dataset in this case that we consider in this case was again a fMRI dataset. We processed the dataset with the same pipeline I showed you before, and we obtained the temporal brain network for 31 participants that were engaged in a narrative task. And this narrative task could be divided with two criteria. The first criteria is the modality. So there were 8 movies and 8 audio. Or they could also be divided by the content, so by the script of the narrative. So 8 narratives were about restaurant situation, and 8 were about airport situation. And so the dataset is balanced by modality and content. And so we wanted to answer to the question which brain areas are the most important in a narrative task. And to do that, we use a machine learning model first to classify the modality and the content of the narrative. And then we used the unexplainable AI technique, which is called shapely values, to understand which subnetwork were the most important in the classification. And after that, we analyzed the result, and we had a new insight on how the brain processes narrative. And so the model we used takes in input the temporal brain network of the subject. It applies a convolutional neural network, and in particular is a neural network that has a three-dimensional filter. And the first two dimensions of this filter match with the dimension of the adjacency matrix. And so the filter was just shifting along the time dimension. After that, to reduce the output of the convolutional neural network, we used a max pooling. And after that, a classifier, so a multi-layer perceptron with two hidden layers. And so with this model, we classify the content, so the airport and restaurant situation, and we classify the modality, so audio or movie. And then we also did the four-class classification, so we were able to say this subject was listening to a narrative that was about an airport situation. And so we use an Adam optimizer, and we train the model for 20 epochs. So now, in a moment, they will be shown the classification result. So as I said you before, we distinguish between audio and movie, restaurant and airport, and we did the four-class classification. And the performance of the model is the accuracy, so the number of correct guesses of the model. And you can see that for the modality classification, the accuracy is quite high, so this was an easy task. And then for the content and the four-class classifications, that we have lower accuracy, and so is a more difficult task for the model. After that, we wanted to understand the importance of the time dimension in our data. And we applied some permutation of the data to understand how this was affecting the classification. And so the first permutation we did was to shuffle the adjacency matrix within the temporal network. And so we were just changing the order of the snapshot in the temporal network. And as you can see, there is a significant drop, especially in the restaurant and airport situation. Then we also permuted the time series at the beginning of our pipeline. So we permute the data before creating the graphs. And in this case, the results are random. So we completely destroyed the data. And then we also wanted to try with the static functional connectivity. So in this step in which we were creating the temporal network, instead of using the sliding window method, we just took a very big window that was overlapping with the time series, and so we obtained just one adjacency matrix, so just one graph. And in this case, the results are quite good, but using the sliding window method was the method that gave us the best accuracy. And now I want to describe you another way to group areas. So we used before brain atlas with the 100 region, and then we use another parcellation to group this region in 7 and 17 subnetwork, which had similar functionality. And this parcellation is the YEO parcellation. And now we will look into details on the 7 subnetwork and their functionality. So we start with the visual subnetwork, which is in the back of our head, and it is responsible for tasks in which we are looking at static and moving object. Then we have the somatomotor subnetwork, which is on the top of our head and is responsible for motor and sensor tasks. Then we have the dorsal attention subnetwork that is active when we integrate visual and audio stimuli. Then we have the ventral attention subnetwork, which is responsible in emotion and sensor. Then we have the limbic one, which is active, which is at the bottom of our head and is active during memory, task, emotion, and motivation and learning. Then we have the control subnetwork, which is responsible of problem decision and decision-making task. And then we have the default subnetwork, which is responsible of story comprehension, thinking about others, and daydreaming. And in order to understand which of these subnetwork, oh, I can go back. Yeah, it's a bit slow. So to understand which one of these subnetwork were the most important one, we use the Shipley value technique. So the Shipley values were introduced in the coalition game context, and a coalition game is a game in which players can work together to achieve a common goal. And Shipley values quantify the contribution of each player in a coalition of players. And this technique is also used in explainable AI to understand which feature contribute the most into a decision of a model. And in our case, our player were the brain areas, and the contribution of a brain area is the performance of the model just considering that area. And in order to select some area within our data, we mask them by setting to 0 the row and column that were corresponding to that region. And so these are the results for the modality classification. So in this case, we are trying to distinguishing between audio and movie. And you can see that the most important subnetwork is the visual subnetwork, which is quite intuitive because we are distinguishing between a context in which the subject was just listening and a context in which the subject was listening and watching. Then we did the same for the content classification result, and so now we are classifying between airport and restaurant situation. And the most important network is the default one, which align with the previous result by Baldassano and Simonai. And as I mentioned you before, the default subnetwork is the one responsible for story comprehension. But then we had another interesting result, which is the temporal parietal subnetwork, which is associated with the bottom-up information processing. So there are two ways to process new information. So the first type is the top-down processing. So we use our knowledge to elaborate the new information we have. But with the bottom-up instead the processing, we don't use that knowledge, but we build on top of the new information we have. And so the temporal parietal subnetwork is associated with the bottom-up information processing. And this result is a step further in answering to the open question raised by Baldassano et al., in which they were saying that the narrative processing is not just a one-way processing, but is both top-down and bottom-up. And then we have the combined classification result. So in this case, we are classifying both the content and the modality. So we are saying it's a movie related to an airport situation. And so the results are consistent with the one I just showed you before, because both the visual and the temporal parietal subnetwork are the most important part of the brain for this task. So in this paper that we published at Network Neuroscience, we proposed a method to identify which brain areas were significant for a task. And for future work, we would like to extend this method for to tasks that is completely unclear which brain areas are important. And then we would like also to analyze, so to repeat the analysis, but considering the connection between areas and not the complete areas. And so that can be done by masking just the connection between the areas and not the complete column and row. And then we would like to analyze the moment, the time step, which is the most important one. And for example, in task that is important the time, such as the one of decision-making task. So now we move on to the last topic, which is machine learning applied to temporal graph. In this context, I was contributing to the graph neural network.jl package, and in particular I did two summer of code, one with Google and one with Julia. And I collaborated with the assistant professor Carlo Lucibello at the Bocconi University. And first I want to introduce you what is a graph neural network. And to do that, I first need to describe you the message passing process. So in machine learning, graph can have additional information at the level of the node, of the edges, and at the level of the whole graph. In this case, we have that the additional information is a vector that is associated with the node, and usually they are called features. And so the message passing is composed by 3 steps, and we want to consider it from the point of view of node A. So node A has a 3 neighbor. The first step of the message passing is the computation of a message. So for each neighbor, we apply a function that takes as input the information of the neighbor and the information of the current node A, and so we compute a message. And in this case, we have 3 different messages. After that, there is the aggregation step, which is the second step, in which we want to collect all this information using a permutation invariant function, in this case the sum, and so we obtain m bar. That in the last step, we use to update the current information of the node A. So we will have another function called update function that takes in input the current feature of node A, the aggregated message, it combined together, and it applied and so update the information of node A. And so a graph neural network is the message passing procedure done in parallel for every node, in which the function of the first and the third step, so the message function and the update function, are learnable functions, and in particular neural networks. And now I want to show you some example of what GNN can do. So the most famous one are graph classification, node classification, and link prediction. So in the case of graph classification, if our graph represents a molecule, for example, we want to understand if the molecule is toxic or not toxic. And to do that, we have the graph, which is some additional information at the level of the node. We apply the message passing procedure several times to update all the information. And then we sum all together to have just one vector that is the called graph embedding, that is given in an input to a multi-layer perceptron, so a classifier that will give us the answer. And the node classification is a similar task, but in this case we want to know a property of a node at the level of a node. So as before, we repeat the message passing procedure several times, and then, for example, if we want to understand the property of node D, we use his information, so his vector, and we give it again as input to a multi-layer perceptron that will give us the answer among several classes. And then we have the link prediction. So we consider our graph, for example, as a social network in which we have that node are people, and the connection are relationship. And in order to know if there will be or not a relationship between node A and D, we use their information as an input to a multi-layer perceptron that again will give us the answer yes or no. And so now I'm a maintainer of the graph neural network.jl package, which is an open source Julia package that is used to can be used to build and train graph neural networks. It has several features, some such as the implementation of common graph convolutional layer. Then the user can custom his layer. It supports CUDA and MND GPUs. It integrates with graph.jl package. It contains several examples of node, edge, and graph level machine learning tasks. And it also contains heterogeneous and temporal graph convolution. And so I mainly contribute in the second two features, so in the temporal graph convolution and in the example. And so now I want to show you the temporal graph in machine learning. So in machine learning, we consider at the moment just two types of temporal graph. One is a graph in which the topology is fixed, but the features change over time. And the second one has both the topology and feature that change over time. And depending on one of these two types of graph, we can design different temporal model. So for the first type of temporal graph, the graph neural network are called spatial temporal graph neural network because we apply a standard graph neural network to the topology of the graph, and then so we model the spatial dependencies, and then we apply a recurrent neural network to the feature of the graph. So a recurrent neural network is a neural network that is designed to work with time series data to model the temporal dependence. And then we merge these two information together to have an answer to a task. And for the second case, instead we So the simplest model is to apply a graph neural network for each of the snapshots of the graph and obtain an embedding for each time step and then combine all together. Or a more complicated architecture such as the Evolve GCN. They use a recurrent neural network but at the level of the parameters. So the parameters of the first snapshot are given to an input to a recurrent neural network, and then the output will be used for the second graph neural network, and so on. Now I want to show you an example. In particular, I added the model, which is a spatial temporal model, to the graph neural network library. And in this case, we have that the graph is representing the brain, but the graph node are the brain regions. And in this case, the topology represents the structure of the brain, because the edge weight are the number of fibers between two brain regions. And then instead the brain activity is given as a time series as feature of the node. And then applying this spatial temporal graph neural network, we obtain these results. So these are the plot for 3 different brain regions. We have that the light green line is the truth, and the left part is the one that is given as training to the graph. And then the right side instead is the prediction in dark green, and in light green is still the ground truth. And so you can see that the predictions are quite good. Then for future direction of the package, we would like to support additional hardware. We would like to enable the multi-GPU training. With the last Google Summer of Code, we are trying to optimize the message passing operation and the support for sparse matrix operation on the GPUs. And the new result will be presented by a member of my team in the next JuliaCon local in Paris, organized by Guillaume. And then we would like to include more layers and examples. And so during these 3 years, I combined temporal graph and machine learning to improve the analysis of brain data. And next week, I will start a postdoc position in the group of Professor Mutzel in the University of Bonn, and I will apply this knowledge to ab initio molecular dynamics. And here you can see a plastic molecule, in particular the polyethylene, which during time change its structure, and in particular with time it become more ordered, and this process can be modeled as a temporal graph. So thank you very much for your attention and being here.
Donc Aurora, le jury a délibéré après ta présentation et la réponse aux questions, et je vais te lire le compte-rendu qu'il a fait sur ta soutenance. Donc on a trouvé que tu as fait une présentation claire, pédagogique et bien structurée, qui a donné une vision synthétique et cohérente de ton travail en faisant bien ressortir les contributions originales. Ces contributions portent sur la combinaison de techniques d'analyse de réseaux complexes temporels et de méthodes d'apprentissage profond, en particulier pour l'étude de l'activité cérébrale enregistrée par IRM fonctionnel. Le jury a particulièrement apprécié que la thèse embrasse une grande variété de champs disciplinaires et de techniques: neurosciences, préparation de jeux de données à grande échelle, conception de modèles de graphes aléatoires temporels, utilisation de techniques d'apprentissage interprétables et développement de librairies logicielles open source. À travers tes réponses aux questions du jury, tu as montré ta maîtrise des sujets sur lesquels tu as travaillé en faisant preuve de recul et de maturité scientifique, notamment sur les perspectives dégagées par ton travail. Pour toutes ces raisons, le jury a toute confiance dans ta capacité à poursuivre avec succès une carrière académique et nous te décernons le titre de docteur en informatique de l'Université Côte d'Azur.
So in the presence of my peers, with the completion of my doctorate in computer science, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principle of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, in my method and my results. Thank you very much.